Welcome to the course on Introduction to Electrical Engineering. We will discuss today lecture 16 on the topic of 3-phase AC circuit part 2. We will start with the introduction. We will talk about instantaneous power in 3-phase system. We will talk then power in line and phase quantity like phase voltage and phase currents, similarly line voltage and line currents. We will talk about power loss in single phase and 3-phase system and 3-phase power measurement methods, like how we measure the power in case of 3-phase circuit, then followed by some numerical examples like. So, starting with the introduction, we would like to cover today the derivation of instantaneous power in 3-phase systems and different methods of measurement of power in 3-phase system. And of course, we say why is it necessary. Of course, we like to talk about to understand and analyze the power consumption in 3-phase system and to understand the measurement of 3-phase power in lab setup using the instrument like wattmeters. So, to understand 3-phase power, it will be easier to first understand the distribution of power in real life situation. In a network consisting of system to generate, transmit and distribute power is called normally we call it a power system. And similarly, an electrical grid is an interconnected network for electrical power delivery from producers to consumers, and a grid can be formed in the scale we call it countrywide grid. This or it can be divided into the part. It can be a regional grid, sometimes it can be a small like we call it microgrid, and maybe individual scale we call it nano grid like. So, there are many concepts like maybe we call it like a even a many country maybe as a having a common forming grid like maybe in Europe. They have a like a grid of many countries connecting to that together also. So, typical example in case of course, in Indian power grid distributed in different region national wide. POSOCO is maintaining. So, and power grid and POSOCO are responsible to really different around 7 regions in the part of for the maintaining complete power system of India, and the control center. Now, you can see how the control system or total control is taken care of the power flow in the complete AC network system like. Of course, we call it the AC power system is not really so good control, but still we have to control directly or indirectly this AC network like or so. So, then we have a like a typically we have a concept of microgrid, and microgrid we have typically a local generation then local load as so that we call it local grid, but of course, it can integrate with the main grid also as you can see it here. So, we have a like a connection to the typically to the main grid, and but we have a local generation like a here the in this microgrid we see we have a PV generation typically, then we have a wind generation, we have a energy storage like battery energy storage, we have a flywheel energy storage, then we have a typically different kind of load like heat load, then we may have a generation from fuel cell or we may have a energy storage like a supercapacitor. So, this system is supposed to, and then we have a several electrical load which are connected to this microgrid, and so we have a generation, we have a load. So, we can of course exchange the power from the main utility grid if utility is present at that moment. If grid is not there, still you can operate this microgrid locally like, because you have a sources, you have a load as well as you have a energy storage. So, it takes care power balance into that like. So, nowadays the trend of this nature is going to be more and more because in many places you might have a the grid may not be that you can call it very reliable many situations. So, you can operate locally. Even at some time we can operate under emergency also, that you might have a building. So, most of the building operates with the DG set as well as nowadays people start putting or rooftop the solar also, as well as you have a battery energy storage system also. Or so, in such situation of course, you have a indirectly kind of a microgrid which of course integrate to the grid also like. Because you say if you are really using a DG set electricity is very costly. Of course, solar is cheap, okay, then certainly and grid is also not so costly as the DG set. So, normally your tendency is to take most of the power from the grid like in majority cases, because your local generation may be by solar or the wind may be limited like also depending upon the sources as well as the you can call it the space or area where you can put either the rooftop solar or otherwise you can install like wind turbine also. Then another concept is of course, with the local is called DC nanogrid. DC nanogrid concept have come, of course, it has been in practice for long, but now has come more popular because the many generation are directly DC, like solar you have a DC and you can have a maximum power tracking. You may have a battery for the typically for energy storage, and then you may have a many variety of the load, as you can see here, like a mobile charger, LED light, BLDC fan, and then depending upon then you might have a motor load. So, you can have convert this DC into AC for feeding the typically feeding the typically AC motor load or other kind of the load. So, concept have come of, and this the DC bus can be either 48 volt or it can be 380 volt, depends on the power level how much you are, but this concept is going to be like day by day encouraging because of local generation, and you may not be connecting it sometime even with the normal grid also, like. So, these concept of different kind of the grid is coming up, like also. So, now coming to this power system typically consists of the following component: the generation system, transmission system, distribution system, and utilization at consumer level. And the classification is primarily based on the function and operating voltage level. As you can see here, the generation, the transformer you are finding, and probably on both the end you can just see here we have a transmission. This is the really backbone of the AC system. Why AC system really won the war compared to the DC system? It is only the transformer which is responsible to allow you the generation at optimum voltage, transmission at optimum voltage, and utilization at optimum voltage, or distribution as well as the utilization of optimum voltage, and that really give the major function here. As you can see the system here, the transmission is at different voltage, normally at much higher voltage. We will see that just like in this diagram, you can have a generation here either by nuclear or hydro or coal. These are the conventional generation which are normally from 11 kV to 13 kilovolt, and this with the help of this power transformer we step up around to 500 kilovolt for the purpose of transmission, and where at the load center we certainly reduce this voltage to typically on the lower side, and that we go of course may be a distribution transformer and secondary primary distribution, and then we come to the secondary distribution which comes to the consumer level. So, that is the complete system. So, you can just see even a different voltage level are there in different part of this power system structure, like also. So, but that is only the transformer action that you can see here is the transformer. We have another transformer, as well as we have a transformer here. So, there are lot of transformer in this power flow, and normally the transformer have a very high efficiency also, in spite it serve the purpose for the you are using in that to change the voltage level mainly, like. So, we have now if you talk about the first component from the power is really generated. So, conventionally we were using the coal, or the typically you can call it coal, oil, gas we were using for typically for this generating system, or maybe even in thermal power stations we are using even the nuclear also. So, they run the turbine at maximum possible speed with the 2 pole generator typically 3600 RPM in North America, because it is a 60 hertz system, and in India we have a 50 hertz system part of the world. So, we operate at with the 2 pole at 3000 RPM this turbine, because they give the you can call it high efficiency of the turbine at highest possible speed which can afford with the this power frequency network, like and then of course, we have this transformer which step up the voltage at the transformer generation end to the voltage which we are talking about, that 11 kV or 13 kV. You can step up to 500 kilovolt, or you can even step up to even up to 1000 kV, because many countries are using even a 750 kilovolt as well as 1000 kilovolt, but of course, in India majority of the line are 400 to 500 kilovolt, like. Then there is a transmission line, high voltage transmission line, the component which we are talking about. Taking at high voltage, certainly the current reduces and cross section area of the conductor also reduces, and that is the benefit. When the cross section area of the conductor reduces, then you will certainly reduce the cost of the transmission line for the same power, as well as it reduces the losses also, because losses are proportional to current square. So, current is reduced and losses in transmission system also reduced, and that is one of the major reason why we go for high voltage transmission system, like. Then of course, we have a distribution substation. We talk about 2-stage distribution, primary distribution, secondary distribution. Other than protection equipment and switch gear, we have a lot of transformer here also in the typically in distribution substation also, or we have a now distribution transformer you can see of different rating, pole mounted, or typically you may be having on the pole itself, maybe like of single phase as well as 3 phase distribution transformer which are mounted on the pole itself, like also. And then we have like a consumer load, how it is connected. Normally, the primary at the distribution and primary is connected in delta, and secondary is connected in star, which makes the neutral point is stable, because because of saturation in the transformer, whatever harmonics are produced, that turbulence circulate in the delta loop. So, neutral point get stable, and which you are able to feed the single phase load on all the 3 phases. We distribute the equal load for different locality, I mean at the time of design, or you might have even a 3 phase load connected, that may not be a neutral connected. So, but in distribution system, of course, you have to keep 3 phase 4 wire system to give the flexibility to the consumer to connect 3 phase load as well as the single phase load. Normally, the single phase load we normally equally divide on all 3 phases by operational, but of course, by design, but in operation you cannot force that all the 3 phases are equally loaded. So, certainly some kind of unbalance is always there in the load side. So, we will talk about that also when we will come to discuss about the unbalanced load also. Then of course, you have many equipment which are 3 phase, like a domestic floor mill or household submersible pumps, or so you have plenty of such loads which are 3 phase nature. I mean typically these two are example with the motors, but large load itself are mainly the energy guzzlers, like typically air conditioning system or many other such related system, they use the 3 phase motors in general, like so. Now, coming to the like a instantaneous power in 3 phase system. So, we can say here it is a 3 phase 4 wire system. You have a 3 phase supply with the neutral, and it goes to the load sometime, but we may not have a all the time going to be 4 wires, sometime we have a 3 wires, like that. Typically, if you are using a either the floor mill or you are using a water pumping system. So, a cable of 3 wires goes, because neutral is not needed in such a load like a 3 phase motors like also. But of course, if you have a like a single phase load, then you have to run the neutral also. But if you have a like a balanced load, as you can see the equal impedance with the same angle, and you have a 3 phase supply. So, you will have a 3 currents, of course, their magnitude may be equal, but certainly the phase will be different, I mean of all the things. So, one is the phase of these 3 currents are different because of the angle of the voltage, but and in spite the angle of the impedance are the same. So, these are the 3 phase voltage which are I mean root 2 into V p into cos omega t, because we have to put this instantaneous quantity in terms of the amplitude. So, V p is the RMS voltage, root 2 is the peak voltage, now amplitude into cos omega t. Similarly, for 3 phase V b n will be root 3 p V p into cos omega t minus 120, and V c n will be root 2 V p cos omega t plus 120. Now, for the balanced load having impedance Z at the angle of theta per phase, as you can see in the figure, the phase currents lag behind their corresponding phase angle by theta, because this theta positive of the impedance means it is a inductive load. So, your current will lag than the voltage, or voltage will lead by the from the current. So, thus the phase current can be written as I equal to root 2 I p, where I p is the RMS current and root 2 will be the root 2 I p is the your typically the peak current or amplitude of the current, and cos omega t minus theta. So, here theta is introduced because it is a lagging current will be there in that case. Your impedance angle is positive V by Z. So, that angle will go up numerator minus. So, that is here I b will be root 2 I p cos omega t minus theta minus 120 degree, and I c will be root 2 I p cos omega t minus theta plus 120 degree, where I p is the RMS value of the phase current like. So, the total instantaneous power in the load is the sum of the instantaneous powers in the 3 phase. So, we can say P will be equal to P a plus P b plus P c, that is the power for all 3 phases of A phase, B phase, C phase, and the power we can write equal to V n instantaneous voltage of A phase, then I a plus V b n I b plus V c and I c, and then we can put the value from the previous equations for these 3 all these 6 quantity like voltage as well as current. So, P will be equal to 2 V p into I p, because root 2 have been there. So, that will both multiplied become 2 and V p I p, and in parenthesis will be of course, the voltage cos omega t and then the current cos omega t minus theta. Similarly, for V phase cos omega t minus 120 and cos omega t theta minus 120 degree, and for C phase cos omega t plus 120 and cos omega t minus theta plus 120. So, these are for 3 phase, and when you are applying the algebraic relation of cos A cos B, then it become half cos A plus cos A plus B plus cos A minus B. So, putting this of course, applying for these relation. So, we can just see this relation comes here P equal to V p I p, that by 2 get cancel out, and 3 cos theta plus cos 2 omega t minus theta, then cos 2 omega t minus theta minus 240, and cos 2 omega t minus theta plus 120, and you can just see these sum of all these 3 you can call it become 0, or you can call it here we are going to put the typical value. So, P will be V p I p 3 cos theta plus cos alpha cos 2 240, sin alpha sin 240 and cos alpha cos 240 minus sin alpha sin 240, where alpha is 2 omega t minus theta. So, it becomes like p equal to V p I p into 3 cos theta plus cos alpha and 2 minus 1 by 2 cos alpha, and this becomes, this get cancel out. So, this becomes V p 3 V p I p into cos theta, where V p is the phase voltage, RMS phase voltage, and I p is the RMS phase current, and 3 represents the 3 phase power, and cos theta, theta is the perfect angle, or you can call it the angle between the voltage and current, which we already considered that the your current is lagging by angle theta, because impedance was having angle positive. Here it is like a current, it goes to negative. So, this is now you very interesting observation is that this power is not function of time. I mean, it is not pulsating with respect to time, and that is the with a basic very benefit. So, thus the total instantaneous power is a balanced 3 phase system, is constant. It does not change with the time as the hysteresis power of each phase does. So, this results in true whether the load is star connected or delta connected, it does not matter. So, that is the major benefit, that you get the constant power, it is not a pulsating power, no more in case of the 3 phase circuit compared to like a single phase circuit like. So, it give a the birth to many concepts to understand why we adopted the 3 phase system. This is the mathematical justification for that, that we are just feeding a kind of constant power, almost like a DC power to the load, not the pulsating power, which really that pulsating power really causes many issues, like one is the typically noise and vibration, and then you do not have a kind of self starting in case of the motors which you utilize, as well as the efficiency is not affected in case of 3 phase, as you have a problem in case of single phase, because you have to make a some arrangement of self starting also in that case. And now coming to, since the total instance power is independent of time, so average power per phase P for either delta connected or load or star connected load is now P by 3, or we can say the average power per phase will be only you have to divide by 3, that 3 factor will not be there. So, per phase power will be V p I p cos theta, and the reactive per phase power also will be Q p into V p I p sin theta, and the apparent power will be also S p equal to V p I p, and the complex power per phase can be again written similar to like a S p equal to P p plus J Q p, and that is V p into I p conjugate, and where V p I p the RMS value of the phase voltage and phase current like. So, that is normally every balance circuit we do the calculation on per phase basis, but this becomes simplified because you do not have a kind of pulsating term here, which is a function of the time like. So, the total average power is the sum of the average power in the 3 phases. So, P equal to P average, P b average, P c, and that becomes 3 times P, because all 3 are equal. So, that is 3 P V p I p cos theta, and that is root 3 V L I L into cos theta. So, in terms of line voltage, this is in terms of phase voltage. For the star connected load, I L equal to I p, because phase current is the line current, and but the line voltage will be root 3 times V p, that is why it is always the root 3, and where in delta connected load the load current line current is root 3 V I p, but the voltage line voltage is equal to phase voltage. So, once it goes to a relation of root 3 in case of voltage, in case of star connection, and delta connection it goes into current, but this remains the same root 3 into V L I L cos theta irrespective of star or delta connection. And similarly, we can say the total reactive power is Q equal to 3 V p I p sin theta equal to root 3 V L I L sin theta. Like that is true for even for reactive power also, in the relation between the line quantity power in terms of line voltage as well as line current like. And the total complex power can be 3 into S p, that is 3 into V p I p conjugate, and that is 3 I p square Z p, and that will be 3 V p square upon Z p star, where Z p equal to Z p at the angle of theta is the load impedance per phase, and also we can say S equal to P plus J q, and that is root 3 your V L I L into at the angle of theta. And remember that V p I p V L I L are the RMS value, and that theta is the angle of the load impedance or the angle between the phase voltage and phase current, that we call it the typically also power factor angle. Now, coming to the power in line and phase quantity. So, we can say balanced phase voltage, all the phase voltage are equal in magnitude and are out of the phase with each other by 120 degree, and balanced load we say the balance phase impedance are equal in magnitude and in phase. So, we can say the power instantaneous power at balance voltage is constant. So, P t equal to P a plus P b plus C, and that become 3 into V m I m by 2 into cos theta, and this become, because these are maximum quantities. So, this become V 3 times V RMS I RMS into cos theta in terms of the phase quantity. And now it is a relation between power line power in line and phase voltage. So, we can say quantity if it is a phase current. So, we represent normally I phase, or we can call it I p, or line current we call it I L, and phase voltage we can call it either V phi or V phase, and line voltage we represent normally V L. So, revisiting the terminology used to define phase and line current and voltage. So, now coming to the like a power in line and phase quantity. So, phase voltage either V phi is the measure between the neutral and any line, that is called line to neutral voltage, and the line voltage is measured between any two of the three lines, that is the line to line voltage, and the phase current we call it the current in each phase of the source or load, and line current we call it the current in each line of the source or load. So, now deriving the line quantity of a delta connected system. So, we can say power consumed by a load is P equal to 3 V p I p cos phi, and since this load is I L, because it is a delta connector. So, line current will be root 3 times phase current I p, and that will be line voltage equal to phase voltage V L into V p in case of delta connection, and therefore, P will be equal to 3 V L upon by root 3 into I L into cos phi, and that will be P equal to root 3 V L into I L into cos phi. So, same as for star connected load, and these quantity are valid for balanced load like. So, now the real power will be P equal to root 3 V L I L into cos phi, and reactive power will be Q root 3 V L I L into sin phi, and apparent power will be S equal to root 3 V L I L. So, note that phi is the load or impedance angle, that is the angle between the phase voltage and phase current, and these equations are valid for only for balanced load. So, now coming to analysis of balanced system, a delta connected circuit can be analyzed via the transform of impedances by the star delta transform, and for a balanced load it states that a delta connected load consisting of 3 equal impedances Z is equivalent to a star connected load with the impedance of Z by 3, which we have already seen into star delta conversion earlier, and this equivalence implies that the voltage, current and powers supplied to both loads will be the same. And this is the typical example, as you see the here the load is star connected. So, impedance is Z phi by 3, and here it is a delta connected. So, it is a Z phi, and we have a relation here Z y equal to Z delta by 3, and that is the relation between the two sets of the impedances of balanced load of star and delta connected. Many situations we like to convert this delta connected load to star or star to delta, depending upon where the calculation becomes simplified like. So, now coming to some of the numerical problems. So, for a 208 volt 3 phase ideally balanced system, as shown in the figure, the magnitude of line current, magnitude of the load line current and phase voltage, and the real reactive and apparent powers consumed by the load, and the power factor of the load. So, here we have a in the diagram the voltage, here the phase voltage given like a 120 at the angle of course 0 for phase A, phase B minus 240 and phase C minus 240 and phase B minus 120, and we have a like a typically line impedance by 0.06 ohm resistance, and then J 0.12 ohm as a inductor balance cable impedance in that case, and we have a star connected load here which is given Z phi equal to 12 plus J 9 ohm, and V phi equal to V line by root 3, that is 208 by root 3, that is 120 volt across typically here. Now, both the generator and the loads are star connected, therefore, it is easy to construct a phase quantity, I mean equivalent circuit virtually in terms of phase quantity. So, phase voltage is 120 at the angle of 0, then you have that line impedance 0.06 ohm plus J 0.12 ohm, and then you have a per phase impedance of Z phi, that is 12 plus J 9 ohm, and from which we can find out now the typically the line current V upon Z L plus Z load, and that is keeping the value we get this as a 120 angle of 0, and then the total impedance is 15.12 the angle of 37.1 degree, and that comes equal to 7.94 at the angle minus 37.1 degree ampere, and the phase voltage over the load will be V p equal to I p into Z p, that will be your current 7.94 at the angle of minus 37.1 degree into the impedance, that is 12 J 9, and it becomes 119.1 typically at the angle of your minus 0.02 degree. So, that is typically you can call it the load voltage, and this voltage little bit differ because from the source voltage because of the source impedance drop, and the small angle is also introduced because of the source impedance. So, magnitude of the line voltage on the load will be V L equal to root 3 into V p, that will be 206.3 volt, and this is small by from 208 volt to, because again the drop in the source impedance like. So, the real power consumed by the load will be P load equal to 3 V p I p into cos phi, and that is 3 into 119.1 into 7.94 into cos 36.9, that is 2270 watt or 2270 watt or 2.27 kilowatt. The reactive power consumed by the load is 3 into V p I p sin phi, that is 3 into 119.1 into 7.94 sin 36.9 degree, that is 1702 VA 1.702 kVAr or 1702 VAR, and apparent power consumed by the load will be your S equal to 3 V p I p into 3 into 119.1 into 7.94, that becomes 2839 VA, and the load power factor is P power factor load, that is cos phi, that is cos 36.9 degree, that is 0.8 lagging. So, now what are the advantage of 3-phase system? We like to discuss that. I mean, why we adopted the 3-phase system. So, a major advantage of the 3-phase system for power distribution is that the 3-phase system uses a lesser amount of wire than the single phase system for the same line voltage V L and the same absorbed power P L, and the two cases of single phase and 3-phase will be compared here in the next slide, considering that the both are having the wires of same material length and the load are resistive, a simple resistive load like. So, here we have a single phase system, we have a 2 line is going from one and returning back, and you have a feeder impedance or resistance of both RR. So, we can say for the 2 wire single phase system, we say I L equal to P L upon V L. So, the power loss in the 2 wire will be P loss equal to 2 I L square R, that will be 2 R into P L square by V L square. So, that is virtually the, you can call it value of I square. So, that is the loss in the your feeders like. And for 3-phase system, 3-wire 3-phase system, as you can see R here, R dash here, just to differ from that, and we have a 3-phase line with the 3-phase balance system and 3-phase balance load. So, we can say I L dash will be I A equal to I B equal to I C, and it will be equal to P L upon root 3 V L, because say we are considering the load as a resistive load just for the case of simplicity. So, the power loss in the 3-wire system will be P dash equal to P dash loss equal to 3 I L dash square into R dash, it is 3 into R dash P L square upon 3 V L square, and it becomes your typically R dash P L square upon V L square. Now, both equations show that the same total power consumed P L and the same line voltage. So, we can call it P loss upon P loss square if we can take a same power and same voltage. So, it is 2 R upon R dash, and where R is rho L upon pi square and R dash equal to rho L upon pi R dash square. So, where we say R and R dash are of radius same, are the radii of the wires, then the we can P loss upon P single phase and P loss at 3-phase will be 2 R dash square upon R square. So, here you can say the loss are more. So, in the same power loss is tolerated in both the system, then R square equal to 2 R square, then the ratio of material required is determined by the number of the wires and their volume. So, material for single phase divided by material 3-phase. So, here we have a 2 pi R square L, and here 3 pi R dash square L, and here we say it is a 2 R square, because remaining quantity carried out, and is 3 R dash square. So, it will become 2 by 3 into 2, this become 1.33, and it means in single phase you have to use the 3-phase more material. So, it shows that the single phase system uses 33% more material than the 3-phase system, and it can be inferred that the 3-phase system uses only 75% of the material used in the equivalent single phase system. In other words, we say considerable less material is needed for to deliver the same power with the 3-phase system than required for single phase system. So, now coming to the unbalanced 3-phase system, I mean your normally the unbalance may be in voltage or it may be current, but normally it is unbalanced load that causes the unbalance in the current only. So, unbalanced system is caused by two possible situations. The source voltage are not equal in magnitude and may differ by phase by angles that are unequal, or second is the second case is the load impedance are unequal. So, most of the time the situation is that your load voltage are not equal, because you cannot force the consumer to connect the equal load all the times. I mean, you might have designed by design you might have given a distributed equal load, but by operation certainly you cannot force all the consumers connected to a particular port to keep equal load all 3 phases. So, in 3 wire system, when the neutral wire is absent, we can still find the line current I, IB, IC using the mesh analysis, and at node N we can say KCL must be satisfy IA plus IB plus IC equal to 0, because neutral is not connected in this case. So, same could be done in unbalanced delta star or delta delta, star delta or delta delta in 3 wire system. To calculate the power in unbalanced 3 phase system, require that we find the power in each phase earlier, and the total power is not simply 3 times the power in one phase, but the sum of the powers in 3 phases. So, to simplify analysis, we will assume the balanced source voltage, but an unbalanced load, which is normally the practice in most of the cases, but since the load is unbalanced, so Z A, Z B and Z C are not equal. So, line current are also determined by Ohm's law. So, IA we call it IA equal to V n upon Z A, IB equal to V B n upon Z B, and IC equal to V C n upon Z C. So, this set of unbalanced line current produce current in the neutral wire, which is not 0, and in a balanced system, applying the KCL at node N give the I n equal to minus in bracket IA plus IB plus I equal IC. So, that is the neutral current. Now, coming to like a 3 phase measurement, power measurement like virtually. So, 3 phase power measurement, we say a single wattmeter can also measure the average power in case of 3 phase system, that is balanced. So, if we have a P 1 equal to P 2 equal to P 3, then the total power will be 3 times the reading of that 1 wattmeter. You can see the photograph of these analog wattmeter which normally have it, but nowadays we of course have a digital wattmeter also. So, however, 2 or 3 single phase wattmeters are necessary to measure the power if the system is unbalanced. So, if we say it is a 3 wattmeter method. So, we have a wattmeter which have a pressure coil which have a large number of turns, okay, and that has a very large resistance. So, that current flowing through the pressure coil or voltage coil current flow ideally it should be 0, because resistance is very high, and the current coil which have a very less number of turns, ideally it must not have any resistance. So, it must not take any voltage drop across it like that is the basic concept, and these 2 coils are responsible to present this wattmeter reading. That wattmeter reading will explain how the wattmeter reading is calculated. So, if it is a just 3 phase 4 wire system, so we can connect the current coil in series with each phase and the pressure coil with that phase to the neutral wire, as you can see here, or typically in this case because here we are seeing this is typically kind of 3 phase 4 wire system, we have a neutral, but here we may not have it may be 3 wire system or delta connected system or no star connected, but no neutral connection there. So, both kind of maybe have a unbalanced load. So, this method can work regardless of whether the load is balanced or unbalanced or star connected or delta connected. So, the 3 wattmeter method is well suited for power measurement in a 3 phase system where the power factor is constantly changing, and the total average power is the algebraic sum of the wattmeter reading, 3 wattmeter reading, we call it P t equal to P 1 plus P 2 plus P 3, where P 1, P 2 and P 3 corresponding to the reading of 3 wattmeter W 1, W 2 and W 3 respectively. So, now coming to another method, we call it 2 wattmeter method, and 2 wattmeter method is the most commonly used method for 3 phase power measurement, and you can see here we keep the current coil in 2 phases R y and pressure coil between that particular phase and to the third line. So, the voltage applied to pressure coil or voltage coil is line voltage, and the current through the typically going to current coil is your phase current or line current, as you can see how the connection is normally made here typically in terms of whether you have a balanced load or unbalanced load, whether it is delta connected or star connected like. Now, notice that the current coil of each wattmeter measures the line current, while the respective voltage coil is connected between the line and the third line and measure the line voltage. So, although the individual wattmeter no longer read the power by any particular phase, the algebraic sum of the 2 wattmeter rating equals to the total average power absorbed by the load, regardless whether it is your star connected or delta connected, balanced or unbalanced load. So, this method is applicable for balanced or unbalanced load, and total real power is equal to the algebraic sum of the 2 wattmeter reading P t equal to P 1 plus P 2. And this 2 watt will first let us take for case of balance case. So, consider balance case and star connected load as shown here, and our objective to apply the 2 wattmeter method to find out the average power absorbed by the load. And you can clearly see the current coil is in series with the line and phase your pressure coil is in across the line voltage. So, we can say assume that the source is in the ABC sequence and the load impedance is Z y equal to Z y at the angle of theta, and due to the load impedance each phase voltage coil leads its current coil by theta. So, the power factor is cos theta. So, we recall that the each line voltage leads the corresponding phase voltage by 30 degree, and thus the total phase difference between the phase current I A and the line voltage V A B is the theta plus 30 degree, and the average power read by the wattmeter W 1 will be P 1 equal to real part of V A B into I A conjugate, that will be V A B I A into cos theta plus 30, because line voltage is 30 degree. You are leading here, and that will be V L I L into cos theta plus 30. That is the reading which P 1 wattmeter give, and the second wattmeter, the rating. Similarly, we can show that the average power read by the second wattmeter 2 will be P 2 equal to real V C B I C star, that will V C B into I C into cos theta minus 130, and that is V L I L cos theta minus 30. And now we can use the trigonometric identity, that is cos A plus B equal to cos A cos B minus sin A sin B, and cos A minus B we can say cos A cos B minus sin A sin B. So, to find out the sum of the difference between the two wattmeter reading P 1 P 2, we can say P 1 plus P 2 will be V L I L, and we can say in bracket if we add cos theta plus 30 cos theta minus 30, and now this will be P 1 P 2 will be, when we expand it, V L I L into cos theta cos 30 degree minus sin theta sin 30 degree plus cos theta cos 30 degree plus sin theta sin 30 degree, and then it comes to P 1 plus P 2 equal to V L I into 2 cos theta cos 30, that becomes root 3 V L I L cos theta, and that is really the 3 phase power, and that is the sum of the wattmeter reading give the total power average power. So, P T equal to P 1 plus P 2, and similarly we can say P 1 minus P 2 will be V L I L cos theta plus 30 minus cos theta minus 30, and this will be P 1 minus P 2 will be V L I L cos theta cos 30 minus sin theta sin 30 minus cos theta cos 30 and minus sin theta sin 30, and or P 1 minus P 2 will be minus V L I L 2 sin theta cos sin 30 sin theta sin 30, and P 2 minus P 1 will be your V L I L sin theta, and that is the reason we can say the difference of wattmeter reading is proportional to the total reactive power. So, Q 2 is root 3 P 2 minus P 1. So, we from this P T Q T we can say the apparent power calculated is S T under root P T square plus Q T square. So, from this reading this we can, by putting root 3 here, we can find out total Q T from this relation, and we can say dividing Q T by P T give the tangent of the power factor. So, we say tan theta will be Q T P T, that is root 3 P 2 minus P 1 divided by P 2 plus P 1. Thus, the power factor calculated by 2 wattmeter will be cos theta equal to cos tan inverse root 3 P 2 minus P 1 divided by P 2 plus P 1, and for unity power factor this theta should be 0, and for that this making this theta 0 your these two should be equal. So, P 1 should be equal to P 2 for unity power factor. So, this will become 0, and that is the reason this cos theta will be 1. So, for unity power factor resistive load P 1 is equal to P 2. So, here we will have some interpretation. Thus, the 2 wattmeter meter not only provides the total real and reactive power, it can also be used to compute the power factor. So, if P 2 equal to P 1, the load is resistive. If P 2 is greater than P 1, the load is inductive, and if P 2 is less than P 1, then we say the load is capacitive. That so nature we are able to find from typically from this slide. So, although these results are derived from a balanced star connected load, they are equally valid for balanced delta connected load. However, the 2 wattmeter method cannot be used for power measurement in 3 phase 4 wire system unless the current through the neutral line is 0. So, we use the 3 wattmeter method to measure the real power in 3 phase 4 wire system like. So, now coming to numerical problems. So, coming to this, determine the phase sequence of the 3 phase voltage V n equal to 200 cos omega t plus tan, 200 V b n 200 cos omega t minus 230 degree, and V c n 200 cos theta omega t minus 110, and of course, here your sequence is negative sequence. Now, calculate the line current here. So, you have a 3 phase voltage, you have a 3 phase star connected load, the balanced load, and you have a balanced feeder impedance. So, in this case you can represent this network as a per phase basis as we discussed it. So, you have a phase voltage, you have a feeder you have a like a phase voltage, you have a like a feeder impedance 5 minus J2, and then you have a load impedance in delta connected equivalent per phase and plus J8, that is for single phase equivalent. And now you can find out I n equal to V n upon Z y, or equal to I a equal to 110 at 0 degree divided by total impedance is 16.115 at the angle of 21.8. So, your current becomes like 6.81 minus at the angle of 21.8 degree ampere like. So, now I b will be same I a at the angle of minus 120 degree. So, it becomes like a 6.81 at the angle of minus 141.8 degree ampere, and I c is I at the angle minus 240. So, it becomes T 6.81 at angle of minus 261.8 degree, that is 6.81 at the angle of 98.2 degree ampere like. So, now coming to the fourth example, a balanced delta connected load having an impedance of 20 minus j 15 ohm is connected to the delta connected positive sequence generator having a VAB equal to 330 volt at the angle of 0. Calculate the phase current of the load and line current. So, given quantity Z delta equal to 20 minus j 15 ohm, that is 20 at the angle in polar coordinate at the angle minus 36.87 degree, and VAB is given 330 at the angle of 0 degree volt, and that is typically the ohm. So, now coming to as a phase current, IAB will be VAB upon Z delta, that is 330 at the angle of 0 degree divided by 25 at the angle of minus 38.87 degree, that becomes your final current comes 13.2 at the angle of 36.87 degree ampere. Similarly, IBC will be IAB at the angle minus 120 degree. So, it becomes 13.2 at the angle of minus 83.13 degree ampere, and ICA is IAB at the angle of plus 120 degree, that is your 13.2 at the angle of 156.87 degree ampere. Now, your line current will be IA equal to IAB into root 3 at the angle of minus 30 degree, IAB multiplied root 3 at the angle of minus 30. So, putting the value, it comes 22.86 at the angle 6.87 degree ampere. Similarly, IB will be equal to IA at the angle of minus 120 degree. So, that becomes 22.86 at the angle of minus 113.13 degree ampere, and IC will be IA at the angle of plus 120 degree, that is 22.86 at the angle of 126.87 degree ampere. Now, coming to example 5, a balanced positive sequence star connected source with the V n equal to at 100 ampere at the 10 degree is connected to the delta connected balance load at 8 plus j 4 per phase. Calculate the phase current and line current. So, given quantity balance, you can call it the star connected load is V n equal to at the 100 volt at the angle of 10 degree, and balance delta connected load is Z delta equal to 8.J4 ohm. So, now coming to phase current, IAB will be VAB upon Z delta, and VAB is root 3 times Vn at the angle of 30 degree. Your 30 degree leading line voltage is 30 degree leading than the your phase voltage. So, VAB will be 173.2 at the angle of 40 degree volts, and IAB will be 173.2 at the angle of 40 degree divided by 8.8 plus j 4, and it comes to your 19.36 at the angle of 13.43 degree ampere. So, you can call it like here it is a VAB. So, VAB voltage across the delta connected load, that is the line voltage, and now we can say your line current IBC will be IAB at the angle 13.43 minus 120 degree angle, and IBC comes 19.36 at the angle of minus 106.57 degree ampere, and similarly IC will be same at 19.36 at the angle of 13.43 plus 120 degree. So, ICA becomes 19.36 at the angle of 133.43 degree ampere, and then your line current IA will be root 3 times IAB, that is at the angle of minus 30. So, it becomes into root 2 19.36 at the angle of 13.43 degree minus 30 degree. So, IA becomes the line current becomes 33.53 at the angle of minus 16.57 ampere. Similarly, IB will be equal to IA at the angle of minus 120 degree. So, it becomes like your 33.53 at the angle of minus 136.57 ampere, and the IC will be IA at the angle of plus 120 degree. So, it becomes like 33.53 at the angle of 133.43 degree ampere. Coming to the sixth example, the 3 phase balanced load in figure has impedance per phase Z equal to ZY equal to 8.8 plus J 6 ohm, and if the load is connected to 208 volt line, predict the reading of wattmeter W1, W2 and find PT and QT, the total active and reactive power. So, you have a typically 2 wattmeter method here. So, you have been given the typically the line voltage as well as you have given impedance. So, you have to find out the current and then you have to find out the 2 wattmeter reading. So, impedance per phase is, so the power per factor angle is 36.87 and the line voltage 208 volt. So, line current is you can calculate it, Z y will be 8 plus j 6 and that is 10 at the angle of 36.87 degree ohm, and I L will be V p upon Z y. So, 208 y by root 3 divided by 10. So, it become 10 ampere, 12 ampere. So, now the power we can calculate P 1 will be equal to P L I L cos theta plus 30 degree, and that your line voltage 208 and line current is 12 ampere cos 36.87, that is theta plus 30 degree. So, it becomes 980.48 watt, and P 2 is V L I L cos theta minus 130. So, it is a 208 into 12 into cos 36.87 degree minus 30, that becomes 2478.1 watt. Thus, the wattmeter 1 reads 980.48 while the wattmeter 2 reads 2478.1. Since P 2 equal greater than P 1, the load is inductive, and this is evident from the load impedance itself, because you can see the load angle is, your impedance angle is positive. And now P T will be P 1 plus P 2. So, summing of these two power will be 3.459 kilowatt, and Q T will be root 3 times P 2 minus P 1, that is root 3 times your 1497.6. So, it becomes 2.594 kVAr. Now, coming to example 7, the unbalanced star connected load is given in the figure, has a balance voltage of 100 volt in ACB sequence, and calculate the line current and the neutral current, where the Z A equal to 15 ohm, Z B equal to 10 plus j 5 ohm and Z C equal to 6 minus 8 ohm. So, line current will be I A will be 100 by 15, that is the impedance Z A. So, this by 6.67 at the angle of 0 ampere, I B will be 100 at the angle of 120, 10 plus j 5, that becomes 8.94 at the angle of 93.44 ampere, and I C will be 100 at the minus 120 degree 6 minus j 8 at the 10 at the angle of minus 66.87, and neutral current is now I N equal to minus sum of I A plus I B plus I C, and putting the value it comes your 10.06 at the rate of at the angle of 178.4 degree, that is the neutral current. So, because of unbalanced load, we have a neutral current flowing into this 3 phase 4 wire network. Now, coming to example 8, 3 wattmeter W1, W2, W3 are connected respectively in 3 phase 4 wire system to measure the to phases A, B, C to measure the total power absorbed by the unbalanced star connected load in figure here, and to predict the wattmeter reading and find the total power. So, we have a voltage here V n equal to 100 volt at the angle 0, V B n 100 volt at the angle of 120 degree volt, and V C n 100 at the angle minus 120 degree, and here the current is virtually calculated from the impedances and voltage. So, I A comes like a 6.67 at the angle 0 degree ampere, I B comes 8.89 at the angle of 93.44 degree, and I C comes 10 at the angle of minus 66.87 degree. And now, we can have a 3 wattmeter reading here. P 1 is real V n I n, because wattmeter current coil is connected in series with the line, and your pressure coil is connected between line to neutral, that is why we take V n. So, it will be V n I A cos theta V n minus I A. So, 100 into 6.67 and angle of both the voltage and currents are 0. So, it comes 667 watt, and P 2 is the real of V B n I B n star, and that is V B I B cos theta V B n voltage V and theta I B. So, it is 100 into 8.94 into cos 120 minus 93.44 degree, that comes 800 watt, and P 3 is the real of V C n I C star. So, V C n I C into cos angle of theta V C n and minus theta of I C, that is 100 into 10 into cos minus 120 degree plus 66.87 degree, that is 600 watt. So, load power absorbed is now P T equal to P 1 plus P 2 plus P 3, that is 667 plus 800 plus 600, this comes 2067 watt, and also from figure the power absorbed by the resistor can be calculated. P T equal to I A square 15 plus I B square 10, that is the resistor watt, I C equal 6, and putting the value it comes again the same power 2067 watt. And from figure the power absorbed by resistor can be calculated, P T equal to I A square into R A plus I B square R B plus I C square R C, and putting the value again it comes to 2067 watt. Like now, coming to example 9, The 2 wattmeter method produces a wattmeter reading P 1 equal to 1560 watt and P 2 equal to 2100 watt when connected to delta connected load. If the line voltage is 220, calculate the per phase average power, the per phase reactive power and the power factor. The total power here is the sum of both wattmeter. So, P t equal to P 1 plus P 2 is 1560 plus 2100, that is 6660 watt, and the per phase power will be P b equal to P t by 3, that is 3660 by 3. So, that is a 1220 watt, and now the total reactive power Q t will be root 2 P 2 minus P 1, that is root 3 2100 minus 1560, that comes to your 1935.3 VR. So, per phase reactive power is Q p P t Q t upon by 3, that is 935.3 divided by 3. So, it comes 311.77 VR, and power factor angle theta equal to tan inverse Q t upon P t, that is tan inverse 935.3 divided by 3660, that comes 14.33, and hence the power factor will be cos theta equal to cos 14.33, that comes 0.9689 lagging, and it is lagging power factor because Q t is positive or P 2 is greater than P 1. These are the references from where we have taken this all the material we consulted, and thank you very much.